additions, the new wrinkles to this quiz. The chart, like I said, hopefully is starting to come pretty quickly. Make sure your name's on it. I mean, obviously shouldn't have to say that, but for some of you, your handwriting or lack thereof, I can figure out who it is, but for the rest of you, I don't memorize handwriting. Let's work through these. Now at the bottom, it asks you to give the formula for a couple different molecules, these 3 different molecules, right? And so, what kind of molecules are these going to be? Look at them. What do they include? A hydroxide, which is one of your polyatomic ions, right? Phosphate, which is a polyatomic ion, and ammonium, which is a polyatomic ion. They're bonded with a metal, and a nonmetal to form an ionic bond, so it's an ionic molecule. But the ionic molecule has a polyatomic ion, which is what kind of bonded molecule? Right, it's a covalent molecule. So the polyatomic ion portion is a molecule that acts like an ion, but it's bonded to its, the components are bonded together covalently. But they bond with another ion to form an ionic bond, so the overall molecule is ionic, while a component of it is covalent. So sodium hydroxide, which is the polyatomic ion? Hydroxide, which has a charge of what? 1 negative, okay? We're going to pair that with sodium. Sodium wants to become what ionically? It wants to become +1. So when it's +1 and hydroxide is -1, the formula is NaOH, sodium hydroxide, because it's a 1-to-1 relationship, 1 positive to 1 negative. Second part, potassium phosphate. The polyatomic ion is phosphate, PO4, charge is 3 neg. With potassium, potassium is also a column 1 metal, so its charge is +1. The formula becomes K3PO4. Okay? Because you take the charge, you ignore the sign, transpose the subscripts. Transpose the superscripts as subscripts. The other way, if you did it the Tyler DeWitt way, you'd look at it and go, okay, I have 1 potassium, this is a +1, this is a 3 negative, I need them to balance, I need more potassium. I still need more potassium. Now they're balanced. K3PO4. And lastly, ammonium chloride. The polyatomic ion is ammonium with the formula of NH4, charge +1, chloride. Do you see that it's not a polyatomic ion? It's not chlorite, it's not chlorate, it's chloride. So it is simply elemental Cl. Chlorine, column 7, ionizes to become what charge? -1. So it's a 1-to-1 relationship again, and this formula is simply NH4Cl. Now the molecule is written following the rules of ionic compounds that even though ammonium is not a metal, it's acting like a metal. Do you see that? It's a cation, it's a positive ion. And so because it's acting as the metal in this molecule, it leads in the formula. It's not going to be ClNH4. It's going to be NH4, the positive ion, Cl, the negative ion. And what's unique about ammonium? For our purposes, the only positive ion, polyatomic ion, that you've had to memorize. Ammonium is the only positive, so everything else is negative. Now, I know some of you on the quizzes like to put negative or positive. Hopefully you realized on the charge section of that quiz, you're supposed to be putting -2, -3, -1. Your 1 and 2 is really hard for me to differentiate between. Remember I told you in math it's going to cost you? It may cost you in chemistry. and I think I know the difference. It's so nuanced. So try to make your 1s and 2s more distinct. All right? We don't talk a lot about chemistry after chemistry class, by the way, so it might seem like, wow, you think they'd have that conversation at home or something. No. Any questions on these three, or at least now do you see what maybe you didn't understand when you did it before? These are ionic molecules formed between, in this case, two metals, in this case, a nonmetal, and a corresponding polyatomic ion. Okay. I'm going to open the other door only because it is quite warm up here. I need to get some of this heat out of the room. I'm full of hot air, and so is the room. So. Let's see. When last we spoke, we were talking about molecular geometries in Vesper, and we were going to do the examples, but I thought rather than walking through the examples, which are in your book, which you as a motivated, studious individual can go through and look at the examples on your own, I thought we'd go ahead and do the on your owns, which also the answers are in the book, but again, not in quite the same detail as the examples. The examples really do hold your hand and walk you through it. And so for those of you that like that or need that, you have that open and available to you. We're going to start on your own 5.4 on page 185. Now, for those of you that stayed for tutoring on Monday, I know we did this, but hopefully, now we've got a day of separation, so maybe it'll seem fresh again, right? A little bit. Let's go ahead and take a look at on your own 5.4. It says, determine the shape and the bond angle of an oxygen molecule. Now, an oxygen molecule. We talked about this case specifically, right? What is an oxygen molecule? What's it made up of? Two oxygens, so it is a homonuclear diatomic, right? Yes, it's covalent. That's a nonmetal with two of them bonded together, so it's a covalent bond. But it is one of our homonuclear diatomics. We have two atoms of the same element covalently bonded to one another. Now, in a moment, this is going to be more important when we start talking about polarity. But for right now, in terms of the bond angle, I have two atoms bonded to each other. Okay? If I ask the question, what is the pivot atom? Is there a pivot atom with two bonded together? No, there's not. There's only two, right? You need at least three to have a pivot atom to form that bond angle. In this case, homonuclear diatomic, a molecule of oxygen is two atoms of oxygen bonded together to form one molecule of oxygen. What does the bond angle have to be? 180 degrees. It has to be 180 degrees. Now, I didn't open up the case over here, but if I need to, if you want me to, I'll get the models out, because it seems not right to spend all those hours making them and then using them for like 2 classes a year. But in any case, hopefully you can visualize that now. We've got two together, one stick between them. It's 180 no matter how you look at it, because there's only two of them. Basically there is no angle. There is no pivot angle. There is no pivot molecule. It is 180 degrees. So it looks like two-dimensionally represented. So hopefully you can see that it's 180 degrees. 5.5. What's the shape and bond angle of a CHCl3 molecule? CH, I know. Excuse me just for a moment. Second period she has. Second period, she has independent study. Could somebody cover second period and I'll go get her? Mm-hmm. Okay. Thank you. All right. Sorry for that. CHCl3 molecule. Okay. So this one we're actually going to take some time and try to build it up, because you may see it already in your mind's eye. But let's go ahead and build the two-dimensional Lewis so we can look at the three-dimensional Lewis so we can figure out the geometry. Okay. CHCl3. We could go through and draw each element that's in the molecule, place the number of dots around it, figure out which one has the most unbonded electrons, right? Or unpaired electrons. But we know right now which one is it going to be. Carbon. Remember, if it's a column 4 or column 5 element, that's generally going to be the pivot, or it's going to be the center. It's got a carbon, so let's start with a carbon. We've got 3 chlorines and a hydrogen to place. Oh, we have 4 attachment points. We've got 4 to place, don't we? Let's go ahead and place them around. Each one of them has to have at least 1 bond in order to be part of the molecule. These already had 7. This one already had 1. Are we done? Mm-hmm. 8, 8, 8, 8, 2. All right. So, what is the shape of the molecule in 3 dimensions? We've got a central atom with 4 things attached around it. So the first thing is it based upon a tetrahedron? Yes, it is, because there are 4 things. 3 bonds, in this case 4 bonds. Remember, bonds, which could be a single, double, or triple bond, and an unbonded pair are all things. And there are 4 of them. Therefore, the shape here is based upon a tetrahedron. Since it's based upon a tetrahedron, the next question is it a tetrahedral? Which is slightly different than tetrahedron, right? Is it a tetrahedral, meaning is it 4 bonds? Yes. So the shape is a tetrahedral. Knowing the shape's a tetrahedral, the rest of it is stuff I've already memorized. I can go ahead and draw it out. A tetrahedron, or a tetrahedral rather, has the center molecule and has the other molecules, or excuse me, has a central atom and the other atoms in this formation. Every tetrahedral is going to look like this basic shape. What the elements are on the outside and what the pivot, those symbols may change, but that's the diagram for the tetrahedral. And I know that the bond angle then, because it's a tetrahedral, is what? 109 degrees. It's 109 degrees between every bond. That's the bond angle. In my models, those bonds are represented by the dowels. So the angle between any 2 dowels, every angle between every 2 dowels is 109 degrees. Okay? The shape and bond angle, what shape and bond angle are possessed by an arsenic trichloride molecule? Arsenic is over here. It's a column 5A element. Arsenic trichloride. Okay, so hopefully you can take the words arsenic trichloride and see it's going to be arsenic trichloride, like this. Column 5 element means I'm going to have a pair and 3 unpaired, right? For 5. Where am I going to place my unpaired? Or excuse me, where am I going to place my paired electrons in a column 5 element? On the top. It's just easier for you. It doesn't have to be, but it makes it much easier when you try to visualize the 3 dimensions. So my arsenic is going to put my, I'm going to put my unbonded pair on the top and my other 3 attachment points for my 3 chlorines, which will lay out symmetrically around the arsenic. So I'm going to go ahead and place my chlorines. I think we're savvy enough now that I'm going to not put all the dots around it. We know there's already 7. That'll make 8. Arsenic has its 8. Every chlorine has their 8. We're done. Next question. Is it based upon a tetrahedral or a tetrahedron? It is, because there are 4 things. 1, 2, 3, 4. So it's based upon a tetrahedron. Since it's based upon a tetrahedron, it could be a tetrahedral, it could be a pyramidal, or it could be a bent. Now, is it a tetrahedral? No, it's not a tetrahedral. It's based upon a tetrahedron, but the first category of tetrahedron is a tetrahedral. A tetrahedral has to have 4 bonded points. The next case is pyramidal. A pyramidal has 3 bonds and 1 unbonded pair, and a bent has 2 bonds and 2 unbonded pairs. So this case, it's a pyramidal. A pyramidal. So this was a tetrahedral. This is a pyramidal. Or, if you think of it, a tripod. It's like a pyramid. It's going to stand up like a pyramid. It's not going to have the extension off the top like a tetrahedron does, or tetrahedral does. It's going to have that unbonded pair on top. Yes? Yeah. 3 dimensions, it's going to be like that. So you put the unbonded pair on top, and one of the elements in the plane, so what this is showing is this unbonded pair, this central atom, and this atom are in the same plane. And this lower chloride here is coming out of the board. This chloride in the back is back into the board. So arsenic trichloride is a pyramidal with an angle of 107 degrees. Determine the shape and angle of a sulfur dibromide. Sulfur dibromide. Sulfur dibromide. Sulfur is a column, was it 6? Yep, column 6, so sulfur. Bromine is a column 7, noble gas. Okay, again, I'm not going to draw all the dots around the bromines. First question, is it based upon a tetrahedron? Yes, it is. 2 bonds, 2 unbonded pairs. It is based upon a tetrahedron. So is it a tetrahedral? No. No, because a tetrahedral has 4 bonds. Is it a pyramidal? A pyramidal has 3 bonds and 1 unbonded pair. The next category is 2 bonds and 2 unbonded pairs, so it is a bent. Now, cheater way of doing this is I can take my 3-dimensional and I can just change my 2-dimensional bonds with that kind of a symbology if I wanted to, right? Because one of them has to come out, one of them has to go back, and my 2 unbonded pairs are in the plane with the central atom. Because it's all just a matter of rotation and turning, you know? If you wanted to keep it straight, keep it strict, like that. Okay? So it's a bent molecule. What is the angle, bond angle, for every bent molecule? Like this, 105. So there's 105 degrees between every bond angle. Oh, by the way, in a bent molecule, how many bond angles are there? Just 1. There's only 2 bonds, right? Over here in a pyramidal, there's an angle between from this chlorine to this chlorine, from this chlorine to this chlorine, and from this chlorine to this chlorine. They're all going to be 107 degrees. Here, from each of the chlorines to all the other, for the chlorines and the hydrogen, between all of them, there's many more angles, but they're all 109. Here, all of them, which is exactly one of them, is 105. So remember that adding or replacing a bond with an unbonded pair squeezes them together, makes the bonds closer. So 1 squeeze takes it from 109 to 107. 2 squeezes takes it from 107 to 105. In each case. The shape and bond angle of an SiCl2O molecule. Is that right? All right. Take a good guess at what the pivot atom is going to be. Try again. Silicon, right? It's column 4 element. I'm going to use the X so as I don't get it mixed up with my electrons. I've got 2 chlorines and an oxygen. I've got 4 attachment points. So I'm just going to pick 3 of them to use initially. For symmetry, because I always think that way, I'm going to put the Cls on the sides. I could go top and bottom, but I'm just choosing side to side. I'll put the oxygen at the bottom. The chlorines have 6, 7 already. The bond makes 8. 1, 2, 3, 4, 5, 6, 7, 8. Oxygen has 6, 7, 8. Chlorine sees 8. Oxygen sees 8. Chlorine sees 8. Silicon sees 8. We're done. First question. Is it based upon a tetrahedron? No, it's not. It only has 3 things attached to it, 3 bonds. A single, a double, and another single. So there's only 3. Since there's only 3 things around it, what is its shape going to be? If I take this and draw it 3-dimensionally, what's going to happen to, what's the effect going to be of these 3 different connecting points, these 3 different bonds? What are they going to do? Just in principle, what are they going to do? Repel each other. Remember, it's valence shell electron pair repulsion. That's the whole principle this geometry is based on. So as these electrons repel each other, these 3 instances, these 3 bonds are going to repel each other equally. What is going to happen to the orientation of those 3 external elements around the central element? What are they going to do? Move apart so that they're evenly spaced all the way around in the molecule. So 3-dimensionally, this is now going to look like and again, I'm going to not draw all the dots for the electrons around it, but you can see for symmetrically, it's going to look something like that. Now, what's the name of this? If you don't remember, let's go ahead and use dotted lines. Let's connect the points. What's it look like? A triangle. And the name is trigonal. It's a trigonal molecule. You have 3 attachments. They're all pushing apart equally. If I take a circle and I break it up into 3 equal parts, it's 120 degrees apiece. So the bond angle is 120 degrees. Right? Now I did look in my notes, and they don't ask you to learn this for this, but there is a case where there's 2 attachment points and an unbonded pair. That is another form of bent. You don't have to memorize that one. All you have to know are the 3 cases that are based on tetrahedron, tetrahedral, pyramidal, and bent. The 1 case of a trigonal, 3 attachment points, and then linear, 180 degrees, which is 2 atoms connected to each other, or 1 molecule with all bonds in a straight line. All right. We move on then. Page 185. We're going to start talking about polarity. Polarity. And what is polarity? I noted as I looked at the 3rd edition, I learned these terms one way. 2nd edition taught them used a slightly different vocabulary to teach those terms, and now here in the 3rd edition they've gone back to the way I learned it. So I may at times say a couple terms which might sound confusing because I had to relearn my vocabulary for the last 2 years, and now I'm going back to my familiar vocabulary to be in step with 3rd edition. So let me just go ahead and acknowledge that up front, and let me write on the board the 2 things that I might say that are actually saying the same thing. You can see there at the bottom of page 185, you've got this term nonpolar, covalent, and polar covalent. Nonpolar and polar. And I believe in the 2nd edition, the phrase that they used for nonpolar was purely polar. Okay? 2nd edition introduced to me the term purely polar. I learned it when I was in high school chemistry and in college chemistry as polar and nonpolar. If I accidentally say purely polar, you're going to have to remember that I'm referring to nonpolar. The difference is basically between polar and not polar. Polar being an imperfect polar, purely polar being a perfect polar. It'll make more sense as we go through it, but I wanted you to at least have this understanding down so that if I go into a spiel and I'm accidentally saying purely polar, you're like, purely polar, what is that? For your book, that's the same thing as nonpolar. Polar and nonpolar. All right, let's go ahead and jump into this. They use a homonuclear diatomic fluorine as the example as we start talking about this idea of polarity. And in any one of the homonuclear diatomics, the case is going to be pretty much the same. Let's go ahead and draw that molecule on the board. We've got two fluorine atoms that we're going to connect to form F2, a fluorine molecule. We're going to take a step back and just think about this concept right now. What are we indicating when we draw the molecule in this way? What does it mean for two fluorine ions, or actually in this case, two fluorine atoms to come together to form molecular fluorine? What's happening between these two? When we say what's happening between these two, we look at this and say they're bonded, right? Hopefully your vocabulary and your understanding is the point where you'd say these two atoms are now bonded together. Okay. So if they're bonded together, what's happening? What's a bond in chemistry? What is happening? What does it mean when two things are bonded? When two atoms are bonded together, what is actually happening? They're sharing an electron. They haven't given and taken, they're sharing. Who owns the electron? Both of them, neither of them, whichever way you look at it. At any given moment, they do or don't own the electron. We're going to get into the very practical nature of what does it mean to share. Are you all good sharers? You know? So maybe for some of you, if you're a really good sharer, if you're really fair, really equitable, you're going to be a nonpolar or purely polar molecule participant. But if you're a hoarder, if you're selfish, then you are part of the polar bonding problem. It's not really a problem, but that's just the idea, the concept. In this case here, hopefully you're looking and saying, I can visualize two atoms of fluorine. Each one of them have 7 electrons. Each one of them want 8 electrons. In order for them to have 8 electrons, they're not willing to give up any. They're only willing to take. They both want to take. Hey, what do we call it when they both take? They have to share. It goes back and forth. And in your mind, you may see 7 electrons with 1 extra electron. Sometimes it's over here, and 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 sometimes it's over here. Back and forth, back and forth, back and forth. They're sharing these 2 electrons. When they have their electron, they're neutral. Now what happens when they get that other electron on their side of the fence? You know, let's say there's this imaginary division line between here. At times, the electron that's being shared from this fluorine is over here. Okay? Right? That's what it means to share, doesn't it? Think about it. The electron is going back and forth. They're going back and forth, back and forth, back and forth. At any given moment, this fluorine will actually have 8 electrons. When this fluorine actually has 8 electrons, how many electrons does this fluorine actually have? 6. Okay? And if we had a stop motion, at that exact moment when 8 are over here and 6 are over here, what would the relative charges between them be? This one has more electrons than that one, right? When this one has more electrons, its charge would be relatively what? Relatively negative, right? So when that electron, you know, when the electron's over here, this side would tend to be negative because it has the extra electron, and this side at that moment would tend to be positive. Why? Because the shared electron is over here. Now what happens in this case is when this fluorine grabs that extra electron and pulls it to its side, it says, cool, I've got my octet. I'm done. And at the very same moment, as that electron goes farther and farther away from this fluorine is getting more and more satisfied that it has 8. This fluorine is getting more and more dissatisfied that it only has 6. So what's it going to do? going to reach back over there, and it's going to start to pull back. And when it pulls back, because it is a shared electron, this electron is going to get pulled back across the fence over to this side. But what happens at that moment? What is the relative charge on this side of the fence? Now it has the electron, right? So it's negative, meaning that this side over here now is at that moment positive. So when that happens, guess what? This fluorine says, I've got my 8. But this fluorine says, it's not fair. I've only got 6. So it reaches across the fence and it begins to pull the electron back. And this thing repeats over and over and over again. At any one given moment, the electron is actually someplace relative to these two. And wherever it happens to be at that moment, that side tends towards being the negative side, and the other side tends towards the positive side. Now here's the thing. If you are one of these atoms, and you're dealing with this back and forth electron, you have this sense of positive, negative, positive, negative, positive, negative, like an alternating current, back and forth, back and forth, back and forth. But if you're not actually there, and you're on the outside looking in, you're looking at this whole molecule. What charge do you see? What net charge is there? Nothing. Are electrons actually leaving the molecule? No, they're not. Are any electrons actually coming into the molecule? No. So there's no change in the overall charge. There only is changes in the location of the subcharges. Remember we said that a neutral charge doesn't mean that there are no charges. It means that the charges are balanced. Remember that? So if we have a bazillion negatives and we have a bazillion positives, the net charge is 0. If you have a bazillion and 1 negatives and a bazillion positives, it's a net -1. Same thing here. There is a momentary charge on one side and an equal and opposite charge on the other side at that same exact moment. So that the electron that's being shared, going back and forth, the sides of this molecule are alternating between being kind of positive and kind of negative to being kind of positive and kind of negative. But it'll correct in just a moment. Just stand by. The electron keeps going back and forth. Okay? But the idea is that wherever the electron is, that side, that area tends to be more negative, and as a result, where it came from tends to be more positive. That's the idea about a bond and in this case, a nonpolar or purely polar bond. In the book here, it talks about, I'm going to read the definition. A nonpolar covalent bond is a covalent bond in which the electrons are shared equally between the atoms involved. Sharing equally. Remember, sharing equally has to do with how much force is being used by that atom to get the electron. How much does it want it? How much energy is it willing to give to get it? And on our periodic properties, we refer to that as electronegativity. Electronegativity is that amount of energy that an atom is willing to exert to get, its desire for. And so what we're really dealing with here is how badly do you want it? And how much are you willing to work to get it? Now here, we have 2 atoms of fluorine. Is there a difference in electronegativity between this fluorine and that fluorine? Is there a difference in electronegativity? No. They're the same thing. Remember, electronegativity has periodic properties. It increases up and to the right. In this case, 2 atoms of the same element have exactly the same electronegativity. So what we're looking at here are 2 people that are sharing something, and they both are exerting the exact same energy to get it. They're actually sharing it, but they both want it and are willing to exert the same amount of energy to get it. Because of that, they're equally matched. And because they're equally matched, the electron spends an equal amount of time at each place. Back and forth, back and forth. One of them is not the electron hog. And if they were, they don't have enough force to exert their will on the other. Okay? That's what's happening here. So, back and forth, equally and evenly shared, back and forth, back and forth. Now, That kind of gets messed up if we have a molecule where we don't have exactly the same electronegativity between the two elements involved. And frankly, on the periodic table, there are no two elements that have exactly the same electronegativity. They have some that are very, very, very close, but not the same. And so you could nuance this and push it to the point to say, hey, the only time it is purely, perfectly nonpolar is when you have atoms of the same elements. Now, in chemistry, they actually go through and in some chemistry courses, you'll go through and compute the differences in the electronegativity, and they set up these little bands. Like they'll say between this range and this range between these 2 points of difference, it's nonpolar. And between that point and this point, it's polar. Understand it's a kind of a continuum of how nonpolar or how polar it is, based upon the differences in strength. It would be like, you know, me having Brandon Bergalt up here and think of an antithesis kind of a person and say, okay, you guys are both fighting over the same teddy bear. Who gets the teddy bear? If Brandon really wants it, frankly, Brandon's going to get the teddy bear, right? You guys know that. But if Brandon doesn't care, then anybody else could kind of take it away from him. I know that's a silly example, but we're really talking about how much are you willing to put into getting it? Or another way to think of it, how much strength do you have to get what you want? When we talk about polar bonds as opposed to nonpolar, this is nonpolar because there are no poles. That's the point. There is no positive side and negative side that stays positive and negative or tends to be positive and negative. It tends to be neutral because it's evenly and equally shared all over the place. Now, the next example they give you in the book is HCl, hydrogen and a chlorine. Hydrogen, chlorine. The same case, right? Hydrogen and chlorine are sharing these electrons, these 2 electrons. Hydrogen had 1, chlorine had 7. Hydrogen says, okay, I'll share mine with you, so sometimes you can have 8, and sometimes I can have 2. Sounds like a good deal at first, because if we really do share, you know, sometimes hydrogen will have none, and chlorine will have 8, and sometimes hydrogen will have 2, and chlorine will have 6. But which one has the greater electronegativity? Now, hydrogen is higher on the chart. Remember, our trend is up and to the right. Hydrogen is a little higher than chlorine, but what's the other direction of consideration? To the right. Chlorine is hugely to the right relative to hydrogen. And when you have, if you have a periodic table that actually gives you the numbers, you would find out that chlorine has a much larger electronegativity than hydrogen does. So what does that mean? Well, if chlorine has a higher electronegativity than hydrogen, what's going to happen is the electron is going to tend to reside where? The shared electrons, where are they going to tend to be? In principle, remember, they're going to tend to be with that element that has the more force, is willing to exert more force to get it. Or which element has the higher electronegativity? In the case of hydrogen chlorine, which one has the greater electronegativity? Chlorine. Where is the electron going to tend to be? With the chlorine. It will occasionally be with the hydrogen. But when it comes right down to it, chlorine doesn't share fair, and it's got the brawn to steal the electron when it wants it. And it'll give a token occasionally to the hydrogen and let it have 2, but hydrogen is going to spend most of its time with nothing, and chlorine's going to hog that 1 electron. So if you visualize it this way, it might be here, and then it's going to be here. And then it's going to be here, but then it's going to be here. And it's going to be here, but then it's going to be here. Okay? Chlorine's going to hog the electron. Now, when the electron is at chlorine side, what charge does chlorine have? This side of the molecule tends to be negative. And when the electron tends to be over there, this side is positive. But here's the deal. Unlike this perfect sharing, even sharing, this molecule, this doesn't experience even sharing of the electrons. At any given time, I would expect the electron to be on that side, right? Chlorine hogs it. If I take snapshots, I would tend to find, most of my snapshots, I would tend to find the electron on that side, which means it's not going back and forth positive and negative evenly. This side tends to be negative more than this side. And so what we end up with is, and the symbol here is a lowercase delta. Delta, delta, it's for partial charge. Partial charge. We set up what's called a dipole. This molecule actually has 2 poles. Why? Because all things being considered, the electron is usually on that side of the molecule, which means that side tends to be negative, and this side tends to be positive. Altogether, it's neutral. It's not attracting any more electrons in or out. It's not attracting any other atoms to try to react with. But within its relationship of these electrons, the electrons tend to be over here because of the greater electronegativity of the chlorine. Because of that, at any given moment, this molecule has a negatively charged side and a positively charged side. And because it tends to have a negative side and a positive side, this is a polar covalent bond. This bond is polar covalent. Why? It's covalent because it's being shared. It's polar because one side tends to be a charge and the other side tends to be the opposite charge. In this polar bond, there is no tendency. It is occasionally positive and occasionally negative, but it's evenly distributed back and forth. One cycle per 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 one cycle. It's a nice non-polar bond. Over here, one cycle to several cycles. One cycle to several cycles. So that side is going to tend to be negative all the time.